Yani böyle biz de mi yapacağız hocam?
Okay, now okay. So observation will be the following. So let, for example, W be a subspace of V. Okay, and okay, spanned by me, so spanned by F1, F I don't know, K, and let E1, En be a basis for V. Okay, now each vector Fi, these are elements of W. So W is span of F1, Fk. So dimension of this is at most K, right? Because if these are linearly independent, then this has dimension K, but maybe they are dependent, so it might have dimension less than K. So dimension of W is at most K. But V is span of E1, En, and dimension of V is N, because I said here that this is a basis. Okay, it's a basis. Now let me write each Fi in this basis. So F1 is what? İlk önce siz yazmayın. Gel bakalım. Kamera, evet. Yok. Ortaya alacağım. Okay, so we are going to prove this observation that applying row operations doesn't preserve the column space, which we showed here in this example, right? We showed that this row operation changes the column space, but we will see that the dimension of the column space doesn't change. Okay, space might change, but dimension doesn't change. Actually, this thing will prove a lot more stuff than just this one. Okay, now let me write each element Fi in this basis. So A1, 1, E1. I want this to be a row, so A1, 2, 2, A1, and row gibi. O yüzden ilk önce yazmayı dedim. Hani kendimden de emin olamadığım için ama genelde yanlış yazıyorum. So we have K many elements. Let's say A K1, E1, A K2, E2, A Kn, En. Aslında buna niye K dedim ki ya? Ona M yapalım. Değil mi? Özür dilerim. Şunu M yapayım. Okay. So we get this matrix A, right? A11, A12, A11, A21, A22, A2N, and AM1, AM2, AMN. Okay. Now, if you apply row operations here, right? For example, interchange two rows. What does it correspond? Changing two rows. You are changing this two generators of the subspace, right? Or multiply a row by some number. It will just multiply, for example, multiply the second row by 2, right? This is a row operation, elementary row operation. It will correspond multiplying this by 2. Or add 5 times this to last column. It will just, you will take this, multiply with 5 and add to this one. So row operations will correspond to operations on this subspace, on these generators, right? Either you multiply a generator with a number or interchange two generators or add a multiple of a generator to another generator. So row operations correspond operations. Okay, let me write like this: elementary operations on the generated set F1 F N. Nedir onlar? İşte sayıyla çarpmak, ikisinin yerini değiştirmek veya birinin bir katını diğerine eklemek. Of course, the subspace will not change because you are just doing operations on the basis elements, but you don't go out the subspace. You are always in the subspace. Değil mi? Yani bu subspace'in dışına çıkmıyorsunuz. Bir vektörü bir sayıyla çarpıyorsunuz, iki tanesini topluyorsunuz veya yerini değiştiriyorsunuz. Subspace'in dışına çıkmıyorsunuz. Okay. You can do another operation. So these operations, as we have seen before, these operations doesn't change the subspace W, right? W doesn't change. What about operations on EIs? On the basis namely, I may multiply one of the vectors with a number I may interchange two of them, or I can add a multiple of one of them to another one, right? The same kind of elementary operations apply to this set. Here we saw that gadget on here fn's, and it didn't change the subspace, but I can repeat the same game with this basis element. For example, let's multiply. So let me have this basis en, but let me multiply one of them by a number. Mesela bir tanesini 5 ile çarpalım. Hangisini? İkinciyi. Right? Let me multiply one of them with a non-zero number. What happens? How the matrix A changes? Well, if you do this, what will happen? Let's just come back to here. So I replace E2 by 5 times E2. So I will have, so this is my E2 prime, my new basis, E2 prime. E1, E2 prime, E3, E4, and En. So then you come here, you have E2 here, but you want to make this E2 prime. Well, E2 prime is 5 times E2. So here I should write 5 times E2, but then not to spoil the equality, I should divide also with 1/5 so that, you know, it doesn't get, I mean, the equality doesn't change. And now this is just E2 prime. So in this new basis, what happened? The second column is multiplied with 1/5, right? So this became 5 here, 5 here, right? If I write prime, then this column is divided by that number. So, okay, so that operation, so this operation change the second column by multiplying with 1/5, right? If you multiply the second basis element by 5, then you interchange, you multiply the second column by 5. Okay. What if I interchange two elements? So I1, let's say I have I, şöyle diyeyim, A1, okay. Atıyorum E5. Let me write it this way: E1, E3, E4, E3, E2, E5. So what I did, I interchanged the second and the fourth basis vectors. What happens here? If I interchange the second and the fourth basis vectors, here I have A1 to E2. Şöyle yapayım. A1 to E3, A14 E4, A15 E5. Same thing, A2 to E2, A23 E3, A24 E4, A25 E5, right? N2, E2, A, N3, E3, A, N4, E4, and 5, E5. Now I interchange the second and the fourth basis elements. Well, what happens? I have to just take this term and it interchange them, right? I will consider this my as second basis element. So it will correspond to what? The coefficients will also interchange. So changing the ith and jth basis elements will interchange ith and jth column. So if you interchange this, okay, E3, E4, E5 with this one. Okay, this operation will interchange the second and fourth columns. Okay, so if you interchange the second and fourth basis element in the column space, second and fourth columns will interchange. Okay. Of course, changing basis elements doesn't change the dimension, right? Changing basis elements corresponds applying isomorphisms because you are just changing basis elements. You obtain a basis from another basis. That's a linear isomorphism, and linear isomorphisms preserves dimensions. Okay, a subspace is moved to another subspace with the same dimension, right? Therefore, column operation, this column operation and the previous one changes the subspace, but it preserves the dimension because they are invertible operations again. Okay, they are just applying some operations to the basis elements, but they are reversible operations. And again, if you add a multiple of a vector to another one, so let's proceed with that one. Evet. Yok, bunlar vektörler, columnlar. So rows and columns are here. These are just some vectors spanning this subspace. What we see here is that if I make a base change in the basis of this ambient vector space, okay, that will correspond to column operations here. It will change this subspace. Turtle, it will be moved to another space, another subspace, but its dimension is preserved. Because what you are doing, you are just changing coordinates. Okay, and they are reversible operations. So you are not losing dimension, but your subspaces are moved around. And what about an operation like this? Let me just, for simplicity. So this is the basis of the ambient space. And suppose I do this. Let's say I want to write this. So what happens? I multiplied the second basis element with 2 and add to the first one. Yani 3'lü çarpalım. Okay. This is the basis. This is another basis. What is the effect on this on the matrix A? Bakalım. F1 was what? F1 was this. A11, A1, A12, A2, A13, A3, A14, A4, right? Now you have, so this is my E1 prime, okay? Instead of E1, I have E1 prime. So here I want to have E1 prime. How can I obtain E1 prime? Well, E1 prime should be this. A11, instead of this, I should have this guy plus this one, right? But if you are adding this, not to change the equality, you have to subtract this. So I have to subtract what? A11 times minus 3 A11 E2. But I have already A12 E2, A13 E3, A14 E4. Now this is just A11 E1 prime. And here what happens? I have A12, the original coefficient. It is changed with this. You subtracted the first column from the second column 3 times, right? Here you are adding the second basis element to the first basis element by multiplying by 3. The effect of that is you are just adding minus 3 times the first column to the second column. So here I have E2, A13, E3, A14, E4. So adding replacing E1 by E1 plus 3E2, right? Which is E1 prime, corresponds replacing the second column, replacing second column, let me write like this, second column by which one? Second column minus 3 times the first column. Okay. So what is the consequence of all of these operations? It's the following. If I have a vector space and a subspace, vector space has bases here, E1 to En, and this is a not necessarily a basis, it's spanning set. I can apply 2 different kinds of operations. I can apply operations on these vectors, elementary operations, meaning that I can multiply one of them with a number, interchange 2 of them, at one of the multiples of a multiple of one of them to another one. They correspond to row operations on this matrix. Or you may apply elementary operations on this basis that will correspond to column operations on this. And these operations, row operations doesn't change W at all. Column operations changes W, but they're all isomorphisms, therefore its dimension doesn't change. The subspace changes, but dimension doesn't change. Okay. Okay. Peki bizim orijinal question'ımız neydi? Row applying row operation doesn't preserve the column space, but the dimension of the column space is preserved. Şimdi diyeceksiniz ki biz row operation'lar yapmadık ki değil mi? Column operation'lar yaptık. Ama column'lara row operation yapmak we want to prove this. Applying row operations doesn't preserve the column space, but its dimension is preserved. Okay, now applying row operations to column space. So, proof of the observation. Burada şunu yaptık. Bu baz elemanlarına yapılan işlemler column operation'larına denk geliyor. Ama so operations on this basis elements corresponds to column operations. However, operations on this basis elements doesn't change dimensions at all because they are all isomorphisms. Okay, they are just you are multiplying a vector space with an isomorphism. You are mapping a vector space with an isomorphism. It preserves the dimensions of all its subspaces. Therefore, dimensions are all preserved under row and column operations. And we will use that observation to prove this one. Applying row operations doesn't preserve the column space, we know this, but the dimension is preserved. Now, why is that? Okay. Observation, bu ikinci observation mıydı? Observation start. Observation start. Group of observation. Well, I have a matrix. I have columns and many columns. So this is an n by n matrix. Each CR is using Km, and the column space is W. It is the span of C1, C2, Cn. And we are applying row operations. Not column operations, but row operations. So we apply row operations to this. Let's say EK, EK minus 1, E2, E1. This is another matrix, right? I multiply A by this elementary matrices. I obtain another matrix. This is also a column space. I can look at its columns. It has a column space. that column space is completely different than this one. But we claim that it has the same dimension. Okay? Why is that? It is because of your translate. Take the, for example, transpose of this. So we claim this column space of dimension of column space of B is the same as dimension of column space of A. Why is it? Well, take this equation. Take its transpose. When you take transpose, multiplication is reversed. So your elementary matrices, this time you take their transposes. They were row operations, but taking transpose interchanges row and column. Now these are column operations, okay? Because you had an elementary matrix obtained from by a row operation, but if you take its transpose, rows becomes columns. So now it's a matrix obtained from identity by a column operation. Okay, and you are multiplying from right, that will correspond to column operations on this. So what you are doing, you are applying column operations to this matrix, and what we see that applying column operations doesn't change the dimension of the column space, right? So okay, yani biz şimdi ne yapıyorduk? Row operasyonlar uygulayınca column space'inin boyutu değişmiyor diyorduk. Row operasyonlar burada column operasyonlarına dönüştü. Column operasyonları da bunların column space'ini değiştiriyor. Tam istediğim gibi değil galiba. Çünkü ben bunun yani A'la B'nin column space'leri değişmesini istiyorum, dimension'ları. Column space'e row operation uygulamak
Bu değiştirmiş. Aşağıdaki. Doesn't change row. Column space'leri, row space'leri değiştirmiş.
Şunu ben bir düşüneyim. Bundan çok emin değilim. öyle gitmek istiyorum da kafam karıştı. Neyse siz de düşünün, ben de düşüneyim. Okay, so I'll fix this next time, okay?
We want to prove that the dimension of row operations is the same of dimension of column operations, right?
Dimensions of column, not column operations, but
The column space is the same dimension of row space.
yes.
We want to prove.
Yeah, here, first I want to prove that row operations doesn't change the dimension of the column space. And then we do the following. Now, finally, suppose I have done this, I have proved this, okay? Finally, let A be an n by n matrix. So it is either you may think it this way, R1 to Rn, or C1 to Cn, right? These are the rows. It gives me the row space. This gives me the column space. And we want to show that row space and column space has the same dimension. So dimension, and how can we prove this? We apply row operations to this, row operations, and finally obtain the row reduced echelon form. So this is row reduced echelon form of A. What kind of matrix is this? This is something like this. There might be some zeros like this. And then we may have something like this. İsterseniz bir tane örnek yapayım. Şöyle mesela. The row reduced echelon form might be this. Okay. Row reduced echelon form oluyor. Now, this row operations, you know, that doesn't change the row space at all, so its dimension is preserved. It changes column space, but dimension is preserved. So the column space of this and A has the same dimension. Row space of A and B has the same dimension. Actually, row space of A is the same as row space of B, but for column space, the dimension of column space of A is dimension of column space of B. And I am interested in the dimensions. So dimensions are preserved under row operations. And what is the column space of this? Or row space of this? What is the dimension? Well, dimension will be determined by this, you know, identity looking gadget, right? So dimension, you will have something like this, some 0 rows, maybe some 0 columns, but you will have this pivot elements, identity looking matrix. And the number of non-zero rows is your dimension. So the row space is 2, has dimension 2. What about column space? Well, if you look at it as columns, so this is one vector, this is another vector, this is another vector, this is another vector. And clearly they form a basis, right? So dimension is also 2 for the column space. So the row space and column space for a row reduced echelon matrix are the same. It is seen easily. And this operation doesn't change the dimensions. Therefore, in the original matrix, the row space and column space is the same dimension. Okay. This also proves that row reduced echelon form is unique. So also is a remark. Row reduced echelon form is unique. Yani ne demek istiyorum? So you started with a matrix and obtained this row reduced echelon form. A friend of yours started with the same matrix, applied different operations, but finally he or she should get the same matrix, the same entries. Why is that? Well, suppose you have this matrix A, and you apply elementary operations, and you obtain a row reduced echelon form. Let's say B, and you take the same matrix, you apply different elementary operations, not the same, E1 prime, E2 prime, and EL prime, not necessarily the same number. Burada belki 5 tane kullandınız, burada 15 tane kullandınız. Yapabilirsiniz, hani uzattığınız iş. And you obtain another row reduced echelon form, let's say B prime. These are the same. Why is that? Well, it is because of the following. Well, since both of them are, so A is what? Okay, so claim is B is B prime. These are row reduced echelon matrices. Okay, now I claim that they are the same. Why is that? Well, what is A? Is just B times EK prime inverse, EK minus 1 inverse, E1 inverse, and A is also E1 prime inverse, E2 prime inverse, EL prime inverse, B prime. Since they are equal, I have this. So this matrix, these are all invertible. Therefore, their product is invertible. So this is an invertible matrix. Let me call it P1. And let me call this matrix P2. They are both invertible. So I have P1B is equal to P2B prime. Since they are invertible, I can just take this one to the other side. P2 inverse P1, B is equal to B prime. Well, this is an invertible matrix. Let's call it P. So P times B is equal to B prime, where both of them are row reduced echelon matrices. Row reduced echelon matrices okay. Have this kind of, columns where you have 1 in each column and zeros everywhere. So if you multiply with this, what will happen? Şöyle yapayım. Mesela diyelim ki şurada P matrisim var. Atıyorum bu 3'e 3 olsun.
Saat 35 mi oldu? Yok, 28.
Okay. Let's say A11, A12, A13, A22, A23, no, A21, A22, A23, A31, A32, A33. And for simplicity, let me take something like this. And then you have some elements here. And here you have another row reduced echelon matrix. But since it has the same bir dakika. A ile çarpınca okay, now multiplying with this corresponds to multiplying with elementary matrices. So this is a product of elementary matrices. So you are applying row operations. Row operations will keep the row space the same. Therefore, I should have a vector like this here, 1, 0, 0. But here it may have something else, and then I should have this. And I should have this also. But these entries may not be the same as these entries. However, if you have identity here and identity here, and if you multiply with this one, so it will correspond to the following. You multiply this matrix with identity and you obtain identity. That forces this gadget to be identity itself. Okay? Yani şunu söylüyorum. Bunun içinde şu vektör olduğu için ilk komponenti 0 olmayan bir vektör olduğu için bu uzay ikisi aynı. O yüzden burada da var. O yüzden burada row reduced formda burada 0 row olamaz. I cannot have 0 column here because then this subspace and this subspace would be different. So I should have one vector with non-zero entry in the first column. But then that will give me a vector like this, and then row reduced echelon form gives me that these are 0, and so on. And multiplying this matrix with this one gives me this, but that implies that this matrix has to be identity. So this P is just identity, therefore B and B prime are the same. Bunlar da aynı. Evet. Niye? Because since P is identity, so these stars are also identity. Okay. This kind of gives a way of obtaining a canonical way of obtaining basis for a subspace. And you give me a subspace, I apply row operations, and then I obtain a basis like this. This is my first basis element, second, third. And this, what we prove, shows that no matter how you apply these operations, you get the same basis. Okay, so in a vector space, you first fix a basis, and then any subspace has a canonical basis. Okay, which is obtained by this operations. Şimdi bu P identity oldu ya, bunu identity ile çarpıyorum. Identity ile çarpıp bunu elde ettiğim için bu x tane.